morning is by Dr. Mark White from the Georgia Institute of Technology, entitled Characterization of Sulfated Metal Oxide Catalysts by Reaction with Isopropyl Amine, and it's co-authored by Dr. D. Su.
It's a pleasure to be here and share with you some of our recent work related to sulfated metal oxides. As many of the preceding authors have talked about in the introduction, I'll make the introduction rather brief and just indicate that some metal oxides have unusual catalytic properties when they've been sulfated, and then with the addition of transition metal ions, the activity can even be enhanced. As far as some of the earlier characterizations that have already been discussed, so what I'd like to do is come right through the characterization that we offer today as another tool to be used in this endeavor to characterize these sulfate zirconiums. And the basis for this tool, the chemistry which we and others use, is the Hoffman reaction, in which primary amines react with protons in solution to form the olefin and ammonia, and then to give the proton back. And it would seem appropriate that we got people going before us saw this as an appropriate titer of proton sites, perhaps on a solid surface. The application that I'll cite is one from Ray Gorty's lab at 10, in which they were titrating ZSM5, HCSM5, with isopropyl amine. And the experiment is to first condition the solid by heating in inert, adsorb the amine, and then note the weight change. This was done in a TGA, but you can also follow these changes in a mass spectrometer. And then the solid's temperature would be increased at a steady rate. And the TGA, the mass of the solid decreases as something occurs. And they noticed two weight changes, two regions of weight change. And we've also noticed the same thing when we reproduced their work. Ray also followed the evolved gas analysis, that is, measured and characterized the gases that were coming off from this. And what he noticed, and we have noticed as well, is that the lower temperature weight change produces gases which are mainly amine, that is, just desorption without any reaction. However, the higher temperature weight change is attended by evolved gases that contain the olefin and ammonia, and that's the signature of the reaction, the Hoffman reaction. So therefore, he and his group measured this weight change at high temperature, and then inferred from that what must have been the amount of amine that reacted. They also repeated this experiment by measuring the amount of olefin that was produced, and we got a nice agreement. And then, of course, from that, one can infer from the stoichiometry what must have been the Bronsted site density. So this technique is used to count Bronsted sites that have a sufficient activity towards this particular reaction. And it's hoped that this measurement might also be in some way related to some chemistry like we've seen this morning. That's the idea in using the tool. Now, we're not the first to have done this. Mark Davis has a paper coming out soon, or will come out, has come out, in which he in fact did the same thing. He did not use a TGA to measure the extent of reaction. He measured the production of the olefin in the mass spectrometer. We produced several catalysts on which to demonstrate the technique. One is a catalyst that we got from Magnesium Electronic, thanks to David Clough and his friends. And we also made our own catalyst, which started out with zirconia from Sigma, and then soaked that in sulfuric acid solutions, either 1 or 2 normal, for different periods of time. As a result of this technique, we were able to generate a number of different solids which had different sulfur loadings, and we'll show the results of that. We also used the technique of producing sulfate zirconium from the oxychloride, followed by impregnation with transition metal ions. And in our case, we use the nitrates of iron, chromium, cobalt, and then we also have one catalyst for chromium and present. We also were able to persuade Ed Coe to provide us some of his unusual catalysts, which were made by the sol gel technique, in which sulfuric acid was the source of the sulfur. And that technique was described in the Journal of Catalysis article, for which we will also take some of his data and show with our with this amine technique, rather, how the reactivity data that he generated in his laboratory maybe correlate the technique that we'll today. And these catalysts were all calcined between 600 and 650 degrees centigrade in air and cool. The procedure, as I mentioned before, is we use small amounts of the sample, which are first heated to 500 degrees C and then cooled back down to helium. Helium is directed through a bubbler containing the amine between the ice point or room temperature. We would record the weight pickup and switch back to just inert only, and then record the weight change with purging of weakly bound material. And then the temperature program would be recorded, would be started, and the weights recorded as a function of time and temperature. It's important that you demonstrate in what temperature range the Hoffman reaction occurs in your system, because it's the weight attendant to this chemical reaction that you're using to characterize the Bronsted site density. And so for selected samples, we would direct the evolved gases into the GC mass spec to ensure that, in fact, when we are measuring a weight change between around 600 degrees Kelvin, that is the place, that's the temperature at which olefin is being produced, and therefore that's the signature of the Hoffman. This is an important test for us to do if you're doing it in the TGA. If on the other hand you carry out the reaction with the mass spec to follow it, it's not necessary to do this. Okay, let's look at some of our data. On this slide, we're showing the temperature in degrees Kelvin on the abscissa, and on the ordinate is the weight of the sample normalized to its initial weight. And we have three samples here. The green line describes the cobalt sulfated, cobalt-promoted catalyst, and that didn't show, but this is the cobalt-promoted one. And the red line is one promoted with chromium, and then the blue line will be the samples which contain both cobalt and chromium. The weight loadings of sulfur are around 1 weight percent, and above the weight loadings of the metals are also around 1 to 2 weight percent. You notice in the cobalt one we have two little regions. We would add the weight changes to both regions because we believe the Hoffman reaction is occurring in both of those regions. And from that weight change, just over this region, we would calculate the density of Bronsted sites. Likewise, we see the weight change here and here, and we use that to calculate the site densities for those samples. A number of catalyst samples have been summarized on this sheet. And on the abscissa is the sulfur loading determined by Galbraith and returned to us. And on the ordinate is the number we would calculate for the micromoles of amine that reacted per gram of solid. First, I want to direct your attention to the series of catalysts that are developed by soaking zirconium oxide in sulfuric acid to develop different sulfur loadings, which is indicated on the abscissa. And then the measurement that we would make would be the ordinate. For one of the samples, I asked the student to repeat it 4 different times in different days of the week and so forth and so on. And the idea is that gives us a feeling and appreciation for the uncertainty in this technique. So that is to say, I would imagine that if we had a point lying off the line or above it, as you see there, then it might be in fact described by the red line. And the red line is nothing more than a curve fit of those data, which was developed by sulfating zirconium, CrO2 that came from Sigma. The one yellow point happened to be the chromium catalyst, for which we now have the sulfur analysis, and it seems to show more sulfur than the samples that we developed just from the oxide. But on the other hand, its proximity to the red line suggests to me that its chemistry, its Bronsted chemistry, is perhaps not unlike the chemistry you'd expect from these samples, but it has more sulfur. And this perhaps confirms in our own minds some of the things we've read in the literature, that the Bronsted site density is in some way related to the sulfur loading. And that's this one point would seem to substantiate that. This green point is one of Ed Coates' catalysts by the sol gel technique. It certainly does have quite a bit more sulfur than we're able to generate in our samples. And it seems to lie very close to that line, which is an extrapolation of the low sulfur loading data. These are made from an alkoxide, and this particular point was generated by calcining at 600 degrees centigrade. One of his other catalysts, which was calcined at 500, but with the same initial sulfur loading, was about where my forefinger is now. That is, obviously it had more sulfur, but it also had less acidity as measured by this particular technique. So the calcination temperature is certainly important, as our preceding speaker had mentioned to us. We also show some more data for the other metals promoted samples, and the zirconia itself has really no acidity measured by this technique, and depending upon the amount of sulfur, you can get different acid site densities. The iron promoted catalyst that we made, perhaps you would argue, is really not much different than the highest loading we had with sulfur, and I would agree with you. But on the other hand, something like the chromium is substantially larger than the ones without the promotion, and with cobalt we see about the same promotion effect. And with the two together, they would seem to be a little bit more. So this tool, in fact, is a quick tool. It allows you to do some measurements in an afternoon or less, and it also permits us to do a qualitative ranking of these materials. Now, one of the other things we were interested in is the strength of the sites. And up to now, I've really not had any data to characterize the strength of the sites. It's just titration. That is with a particular reaction. You're familiar with another but much stronger base that people have used to titrate OH groups on the surface, which is hexamethyl disilazane. That reacts with OH groups to form ammonia and then recycle ethers. This is an excellent reaction for doing on a TGA because the resulting surface species is so heavy, it gives you a large increase. This will also titrate Bronsted sites in silica alumina, so it can be used for strong and weak surface OH groups. So we chose one of the metals, the metal sulfated zirconia, and we recalling to you that the earlier measurement using the weak isopropylamine base, the weak base isopropylamine gives a certain site density of around 140 micromoles of protons per gram of solid. And when we use a sample from the same lot, we're using this much more aggressive base, hexamethyl disilazane, the number comes out to be very close. And so what I would suggest is that in these samples that we're reporting today, this particular sample, is that there are very few weak acid sites or weak sites like OH and silica, but apparently most of the sites that are there are sufficiently strong to catalyze the Hoffman reaction on this solid. I'd like to go back for a moment and share with you from Ed, the paper by Ward and Cody, some of the data that they had presented in that sample, in that paper, was the reaction rate with the butane isomerization, and that reaction rate is reported here on the ordinate. The other data that they had presented in the same paper was a characterization of the Bronsted to Lewis site ratio by using titration with pyridine, and then looking at the infrared spectra and ratio in the areas under the curves. So I just took the numbers right from that paper, and Ed was kind enough to send us some of the solids that he had used in that same paper. And as a result, the data that we generated are on the abscissa of this chart, and the data that Ed and his lab generated is on the ordinate. And for several of these samples, like the three that I'll point out on the forefinger, this one here, and this sample here has Bronsted Lewis ratio of 0.68. Those three data points would seem to describe a single line, which when extrapolated down to the zero reaction rate, comes very close to two of the catalysts, which he reported to be dead, or very, very low reactivity. So taken together, those points would seem to describe a single line, but the one point that Ed was very interested in having us look at was the one that's quite a bit off this line. This had been calcined at lower temperatures, around 500 degrees C, but it had a Bronsted to Lewis ratio of 0.45. Now, from the acid site measurement we would make, it would suggest that it should have low reactivity, but the actual reactivity is much more. And this is an example of how this technique can help to unravel some of the different aspects of the Lewis and Bronsted catalysis. That is, we have a tool which would define the Bronsted site density, and then that would then allow you to compare it to catalysts which have different populations of Lewis sites. This sample that's quite a bit above the line would seem to have more Lewis sites than the points that are near the line. So that's just one demonstration of one of the ways that we use this technique. And now for some conclusions. I hope we've provided some data for you that would suggest that this technique can be used to demonstrate the response of the system for sulfur loading, and that whether you use the oxychloride, the oxide, or the sol gel, the intrinsic chemistry that's there are very similar, but of course the sulfur loadings are quite different. The addition of metals appears to increase the site density by increasing the sulfur loading. That is, you just have to be able to build more sulfur in the sample. And secondly, the activity of the butane isomerization at 280 seems to correlate well with the Bronsted site density when the Lewis to Bronsted site ratio is constant. Unfortunately, this technique tends to overcount sites. That is, for the butane reaction, the technique counts sites which react with the amine which are inactive. And that's the reason why the intercept is well along the x-axis. The intercept at zero rates around, I believe, 120 micromoles per gram. So it's obviously not a desirable technique from that point. That is, the curve doesn't go through 0, 0. But on the other hand, it indicates that there is some relationship. The activity of one sample apparently is greater, which has a greater Lewis site population. And this result suggests that Lewis acidity plays a role in catalysis, which I guess everyone else has talked about today in some way. We thank those people that have helped us make this possible. Also thank Ed for giving us some samples, and also David Clough for giving us samples from MEI. Thank you for your attention.
Thank you very much, Mark. Questions? Yes?
I tried determination of surface by using ammonia. Ammonia changed the structure of sulfate zirconia. Sulfate zirconia changed color in green one. I thought the structure changed to some other. So we gave up, and I took pyridine for characterization. I already published 2 years ago in Translator, and ammonia is also stable as propyl. And I remember that some Korean people also published the determination using isopropyl amine. I think they said isopropyl amine changed structure. So I wonder if isopropyl amine is correct or not for determination.
The comment was that previously people have indicated that the use of certain titrating agents changed the structure. And I'll try to comment on what we have seen. The sample does not appear to change color. It doesn't turn green, and it also doesn't turn gray. The weight of the sample, after it's been heated to the final temperature is very, very close to the weight of the sample before the amine was adsorbed. And so there's no residual weight increase in this sample as a result of this reaction. That is, we don't believe there are materials staying on the surface. I haven't done any other characterizations, so I can't comment on how the surface structure might change.
I'm glad you use pyridine.
Pyridine. Okay.
Any further questions? Well then, let's thank Mark again for an interesting talk. That, as those of you who were here initially this morning know is the end of the session for the morning. Peter Moles regrets very much that he was unable to come, and so we will adjourn the morning session. The afternoon session will begin at 1:45, and we do encourage you to come back. I think that we'll have an interesting afternoon of discussion.